Yeah, thanks everyone for being here. Thanks to the organizers. It's been an amazing conference. So as Guillaume told you, I'm going to tell you about like some hyperbolic surfaces in large genus compared to combinatorial maps. So I'm sorry, my computer died today, so there's still a few typos in the slides, including the title. So if you're bored, you can spot the typos in the slides. So this is joint work with Svante Jansson, who is in Uppsala in Sweden, but I need to thank a lot of people, especially in this room, for very enriching discussions who made this talk, well, definitely less naive and maybe more interesting. And yeah, I apologize in advance because the first part of the talk is going to go quite slow. It's still going to be very introductory. So I guess like a big fraction of you know all about what I'm going to say, let's say in the next 20 minutes. So don't worry, I'll wake you up when it gets interesting for the ones who know everything. All right, yeah, let's get started. So definitions. I'm going to start with maps, which are the discrete surfaces in the title. So Guillaume introduced them like 1 hour ago, so I'm going to try to browse through it very quickly. So as he said, maps are just discrete surfaces that you can build out of gluing polygons along their sides to create a surface. So here I'm restricting to surfaces that are compact, connected, and oriented. And yeah, it's completely combinatorial. There's no notion of geometry yet. And of course, the genus of the map is the genus of the underlying surface, is the number of handles. And I guess you all know about this. So here's an example of a map of genus 1, so a map of the torus. This is the identification of the edges, and then you get a graph drawn on this torus. And again, we distinguish an oriented edge that we call the root. This is for symmetry reasons, to help for counting and so on and so forth. All right. So today I'm going to talk to you about random maps. Guillaume has made, again, a very good introduction about all of this. So the rough question is always, what does a large random map look like? And then depending on what you want to study, you make these words more precise. Large is just always the number of polygons that constitute your maps. And yeah, the classical setting is that you're going to take uniform maps of the sphere. So if I want to build a sphere out of like, I don't know, 2 n triangles, there's a finite number of ways to do it. And then I pick one at random uniformly. And then I send n to infinity. What happens? And perhaps the most famous result in the theory of random maps is the result of Grégory, who's here along with Le Gall, which is the scaling limit of maps of the sphere. That is the Brownian sphere. So here's a nice picture by Jérémy Bettinelli. And I guess from Tim's talk 2 days ago, we know that, well, the Brownian sphere is closely related also to hyperbolic surfaces. So that's already one link between maps and hyperbolic surfaces, but in a planar setting. And I'm going to tell you about another link between maps and hyperbolic surfaces, but in a different regime, which is the high genus regime. All right. So yeah, now the question changes a little bit. Now you want to look at uniform maps of size n and genus G, and you still want n to be large, but you also want the genus G to be very large. So you send both things to infinity. Well, I know this is not very precise. You have to specify a rate of convergence, but I'll sweep that under the rug for now. And again, well, Guillaume has said everything that's on these slides, but there's a certain notion of average discrete curvature, and you can calculate it, and it's negative, so you can expect some sort of hyperbolic behavior. And in fact, this is the case, and we already have a few results about this. And so here's a list of people who have worked on hyperbolic of maps in high genus. So most of them are in this room. There's Omer, there's Thomas, Guillaume, Nicolas, and I guess just Svante Jansson and Gora Brahe are not here today. And here's a nice picture that was made by Nicolas of the local limit of high genus triangulations. Again, Guillaume told you all about this. All right. Yeah, there's still several open questions that remain. Some global properties. So the diameter is done, as Guillaume told you, but you can also always look for the size of certain cycles, like the systole, the separating systole, and you also need asymptotic enumeration. And I saw Thomas being a bit dubious. Yeah, you can also look for the constant in front of the diameter. So when I said the diameter is done, you were not very pleased. Okay, there's still some things to do with the diameter as well. Yeah, all right. But I'm not going to talk about high genus maps in general. Today I'm going to specify a very specific model of maps that's simpler. It's unicellular maps. Guillaume told you about it. Unicellular maps is mapped with only one face. So if you want, you just take, it's maps that are built out of a single polygon. So here you have, do you see that? Oh yeah. You get a map of the torus with only one face. So that's just the identifications of the side of the polygon that will give you what you want. And I want to require more on these maps. I also want these maps to, my maps to only have all vertices of degree 3. And if I specify the genus and the number, like the degrees of the vertices, then it forces me to have a certain number of edges, which is 6g minus 3, and also a certain number of vertices, 4g minus 2. And then, so I have a finite set. As I told you, there's a finite way of like wrapping up a polygon, especially if you require it to have a certain genus and a certain degree of the vertices. I take it uniformly at random, but I will put a metric on it that's slightly different from the one that it's commonly used. Commonly, you just take a random map and the metric that you put on it is just a graph distance. Here, you put random lengths on each edge, independent IID, with an exponential law of mean 1. And the goal is to study this model of maps as the genus goes to infinity. All right, any questions so far? Yes?
Who is the Egan who generated the picture on the first page?
What's that?
Who is G. Egan who generated the picture on the first page?
Good question. I think I found it on Wikipedia or something. And there was his name. I think it's a mathematician. I think it's Gregory Egan.
The author.
What's that?
Greg Egan, the author?
The what?
Author.
The author.
Write books.
Maybe. I don't know. I have no idea. I think, yeah. Wikipedia. I think that's the Klein quartic or something, but I'm not sure. Yeah. Bram nods. So that's it. All right. Yeah, so our goal will be to study this model of random unicellular maps as the genus goes to infinity. And we're getting back to it very soon, but I'm also going to introduce hyperbolic surfaces. Okay. So, well, sorry for all of you who know about it much more than I do. I hope I will not say too many wrong things. So a hyperbolic surface is just a surface that has a metric that gives a constant curvature -1. It looks locally like the hyperbolic plane. And the simplest hyperbolic surface that you can get is the pair of pens, so a sphere with 3 boundaries. And if you specify the length of the boundaries, then there exists exactly one hyperbolic surface that is a pair of pens with these boundaries. Yeah, so that's going to be the building block of our bigger hyperbolic surfaces. And yeah, if you have a hyperbolic surface of genus at least 2, now I take it like compact, closed, no boundaries, I can cut it up into like small pieces, namely pair of pens, by choosing a collection of simple closed geodesics, 3g minus 3 in total, and it divides it into a certain number of pair of pens. This choice is not unique. It depends on the pens graphs that you choose. But so I can divide my. It's very annoying, this thing that's flying over my. Well, whatever. You can divide your surface into like a lot of pair of pens, and yeah, if I want to recover my surface, I obviously need to specify the length of each curve, but I also need to specify like how you glue them back together. So like you could glue them like this or like that. So there's a parameter that's real, that's called the twist factor. And it determines the surface uniquely. So which means that the space of hyperbolic surfaces of genus G, so the Teichmüller space, I'm voluntarily remaining very vague about what it means to be the space of hyperbolic surfaces. It's just parameterized by these coordinates, which are the Fenchel-Nilsson coordinates, the length and twists. And so it's just r plus times r to the 3g minus g. Okay. And so once you have this nice Teichmüller space, which has nice coordinates, you're going to take something more complicated. You're going to quotient it out by all the possible isometries to obtain the moduli space. And these isometries are not easy to understand. So, and in fact, like the thing that you obtain, like the moduli space is no longer a manifold, like the Teichmüller space is an orbifold. So it's like you're wrapping up, like you're like gluing it up, identifying stuff, and you get singularities. So it's a little bit messy. However, there's still nice results on it. So I think the main one is a result from Wolpert in the 80s, saying. So now my Teichmüller space, since I have coordinates, I can just take the Lebesgue measure. God damn it. Okay, well, you see it. You can just take the usual Lebesgue measure on the coordinates, so the product of the dli's, d tau i's, and it gives me a volume form. And the cool thing is that when you quotient out by the isometries, well, it descends to a measure on the moduli space. That turns out to be the Weil-Petersen measure. So if you were at Eileen's talk, you remember she defined it with some Beltrami differentials. So it's all very complicated, but a good thing is that it's just a quotient of the Lebesgue measure. It doesn't depend on the choice of curves. And something that's very good when you want to do probabilities, that the volume of the whole space becomes finite after quotienting. So then you can do probability. You can make sense of what it means to have a random hyperbolic surface, and this is what we call the Weil-Petersen measure on hyperbolic surfaces of genus G. And so you can sample a random hyperbolic surface. I'll call it SG for this talk. And yeah, like, well, it's 10 years ago, 15 years ago now, like people started to try to study the geometric properties of SG as the genus goes to infinity. So we can thank Mariam Mirzakhani and also Hugo with Gut and Young for starting the trend, and it hasn't died out, I must say. So yeah, so that's for hyperbolic surfaces. I hope I didn't say too many mistakes. So there's one typo, is that the volume here needs rescaling by some factorial. You don't really care for probability and sampling, but when you compare the volumes of different genera, genuses, then it's going to matter. So I don't remember exactly what's the factor, but I guess it's like 6g factorial or something. Whatever. All right. So yeah, today the main result, so you can wake up if you were not listening to the introduction. The main result I wanted to tell you about is a strange numerical coincidence that I hope hides something nicer. And I'm going to tell you about it right now. It concerns the counting of curves, of short curves on the surfaces. So yeah. A couple of years ago, Mariam Mirzakhani and Bram, who's here, counted the number of simple closed geodesics in SG, so in the random hyperbolic surface of a given length. And it turns out that it converges in distribution to a Poisson law of this nice parameter that you see here. And 2 years ago with Svante Jansson, when I was in Uppsala, we studied the same thing, but on our model UG. So we studied now the number of simple cycles of a given length. And it turns out that it converges to the same Poisson law with the same parameter. So to be honest, we didn't study UG exactly. We studied a more complicated model, but when I talked with Nicolas and also Cyril Marzouk and Igor Korczymski, it turned out that you get the same result with this simpler model. But whatever, so it's very surprising because we get the same parameter. So the fact that you get a Poisson law is not surprising at all. When you count curves, it's always the same, except when you have like something very wild. But the fact that it's the same parameter and it's also like two models of high genus geometry that are also related by some other works, I don't know. We would like it not to be a coincidence. Maybe it's only a coincidence, but let's have faith that there's something nicer hidden underneath. One just technical point is not only Poisson convergence, it's also like we actually get a Poisson point process with this intensity. So Anna defined it 2 days ago, what a Poisson point process is. So basically it's this plus independence if you take multiple intervals that don't intersect. All right. And so my question is, okay, we have the same counting of curves now. Can we make sense, can we like come up with a conjecture, like in general, if you have like two observables that asymptotically match, you want to say, okay, well, asymptotically, maybe these two models are the same, but it needs to be made more precise because one model is just like graphs on the surface, and another model is just surfaces, complete surfaces. So the question I can ask today is, can we find a way to embed my random map on the hyperbolic surface, so exactly or asymptotically, such that also like the short curves, the short geodesics, they live on the graph. So that's even more, that's a big requirement. So that's why it's very surprising. I still want to have hope. So you can rephrase this question as, if you cut along the graph, well, can I see my surface SG as the gluing of a hyperbolic polygon that I give you? Like, so if I give you a map, it gives you the law of the gluings, then I get the law of the edge lengths as well. There's something that's missing, and that's something that I don't know, I have no guess for, is that if you have a hyperbolic polygon, you also need to specify some angles. And a lot of them have to be angle pi, actually, because if you have a curve, like a map that carries some geodesics, and this map is like cycles with several vertices on it, like at each vertex it cannot have a sharp angle, otherwise it's not a geodesic. And it's exact counting, so you cannot even come close to the graph. Yeah?
Do you want to decide if you're doing before you get your random edge length or after?
It's IID, so you decide your gluing, you decide the random edge length on the polygon. The only constraint is that if two edges are going to be identified, they have to be the same. So in some sense, yeah, you decide the gluing, and then you put, because you have twice more edges on the polygon than you have on the map. But that's the only constraint. The rest should be completely independent. Okay. Any questions so far? Yeah. Sorry, can you speak louder? Yeah. Yeah. What do you mean the metric? I mean, if you just look at the map on you mean on the polygon that's inside? Yeah, so that's what I'm saying. Like if you imagine that it's a gluing of a hyperbolic polygon, and you do the edge lengths, like if you specify the edge lengths of the polygon and some angles, of course there's some compatibility condition. You cannot take any angles and any length. Then yeah, it defines everything, because then it's just you cut out a piece of the hyperbolic plane and then you glue it together. I don't know if that was your question. It's,
if we consider one loop in UN, the edge length to satisfy the triangle inequality, the maximum should be less than the sum of the other edge lengths.
No, I don't think so. I don't think so. You can always put a metric on a graph, and it just means that all the yeah, if you have like a geodesic, if you have a geodesic cycle, yeah, you have this triangle. No, that's not even true. No, geodesic just means locally simple, locally shortest path. It doesn't have to be. You have geodesics that are, yeah, you can go to x from x to y by many geodesics, and some are longer than others. But that's a little troubling. Yeah, yeah. Any more questions? Okay. So, and what that would imply, if we're very like, I don't know, if you have a lot of hope, is that maybe that gives you an asymptotic parameterization of the moduli space that's nice and tractable. So maybe the law of the angles is very, very wild. I don't know. But in this case, yeah, you just get a gluing of a polygon. We know that you can parameterize mg by gluing of some polygons, but the law is completely crazy. So maybe asymptotically the law gets nicer. I don't know. And also, if the correspondence is strong enough, maybe you can import techniques from one world to the other. Like maybe you can import random map techniques, which in our case of unicellular maps boil down to random tree techniques. I will tell you about it later, to the hyperbolic surface world. I don't know. And so yeah, if I try to, I tried to think about it, like, but I didn't make much progress on this question, but now I want to submit these ideas to you, and then you go home and you solve my conjecture. Where can you find a map on a hyperbolic surface? You can just pick a point arbitrarily, and then you look at this point in the universal cover. That's just a hyperbolic plane, and so there's going to be multiple copies of this point, and then you do a Voronoi tessellation. So you divide it into regions which are closer than the others, and then the boundary are drawn it here in purple, and then you go down. So you go down, and this tessellation here, like, there's going to be some identification, and with high probability, if your surface is typical, your map will have only one face, well, by definition, because it's only one polygon, and all the vertices will be of degree 3. So that's, I think this thing here is called a Dirichlet domain, and also if you do this thing when you have one cusp in your surface, and you start from the cusp, it's called the spine construction that Timothy told you about on Tuesday. So yeah, so that would be one way to find maps on my hyperbolic surface. However, problem is that this thing is piecewise geodesic. So like the edges are geodesic, but there's no reason why the angles would be 2 pi. And if you want a cycle in my map, sometimes it goes through several vertices, and if at these vertices the angles are not pi, it cannot be a simple closed geodesic. And also the problem is that, okay, I can do this with one point in my surface, but then I can do it anywhere, and this map here will vary a lot. But I want my map that's embedded in my surface to carry all the short closed, the simple closed curve, the short simple closed curves. And except for a miracle, like when you move this point, well, this thing would move a lot and would not like stay exactly in some places. But this is just like a guess, like a proof of concept guess. But if I'm wrong, please tell me. But the piecewise geodesic is a bit concerning to me. However, this is a new question for us. Take this model. What's the law of the underlying unicellular map? Like, combinatorially, is this thing, if you forget about all the lengths, is this thing just uniform among all the possible triangulation unicellular maps with degree 3, or not? Or is it a nice distribution? And then what are the edge length distribution? Okay. There's another way of finding maps on surfaces, and we learned this in Elise's talk. It's something due to Norman Doe. Now you take a a map with a boundary, just one boundary, and you fix the genus, you fix the, no, it's not a map, it's a hyperbolic surface, sorry. You fix the hyperbolic surface, the genus, and then you look at a surface with like a boundary of length L, and then you take L to infinity. So basically the boundary is going to take up, like it's going to grow, and it's going to get closer and closer to itself. And if you do some proper rescaling of the edge lengths, you get, well, a random metric map, again with only one face because there was only one boundary. And the measure on these things is the Lebesgue measure on the length, just condition on the total length that you impose. So you just like the L rescaled. And yeah, so this is a result of Norman. And the thing is, if you rescale it to 12G or 12G minus 6, exactly, asymptotically, you recover the law of UG. And why Vincent here pointed it out to me is that if you have like a lot of variable on a simplex, and then the simplex gets like a dimension that goes to infinity, it's almost the same as exponential laws with the right average. So actually the law of our UG is just the law of like the ribbon graphs of the combinatorial combinatorial moduli space with one face when you condition it to have a length 12G. And so this has been extended, as we learned because Minkun told us about it. They extended it to any number of faces with Alessandro, who's here, and Simon Barazer, who's not here. And they also used a very different method. And so, yeah, this is troubling. So the question also is that, is it just this coincidence, this numerical coincidence explained just by the fact that you pull back the Weil-Petersen measure to the combinatorial moduli space? I gotta say it's not clear to me, and I asked all the experts in this conference, and it was not clear to them because there's this rescaling and then the flow. I mean, it's yeah, it's kind of weird. So like, if any of you has any idea about this, I'm very interested. So yeah, that's yeah, I'll let you like look at this a little bit more before I move on to the final section of my talk. Any questions so far? So that's basically all my ideas about this coincidence. And now I'm going to tell you a bit about the idea of the proof. Okay. All right, so if we're okay, let's continue. So I'm going to just tell you a little bit about the proof, how it goes, both the theorem of Bram and Mari-Mezahani, and also ours. So this is going to be very low level. So the key principle is the method of moments. I guess, again, most of you know about it. But if you have, under some reasonable assumptions, you have a sequence of random variables. If all the finite moments converge to the moments of a given random variable, then this converges in distribution, this xn converges in distribution toward x. So this is, again, under reasonable assumptions. I'm not getting into that. And yeah, and so how you can calculate moments. So at the origin, I'm a combinatorialist. So for me, probabilities are just fractions. So I just count. So if x counts curves of a given length, then the expectation of x to the r is just, well, the number of surfaces with r marked curves divided by the number of surfaces, roughly speaking. And then, so I said the Poisson law is not very surprising. Poisson law just means that if you have a finite number of cycles that you take at random, you condition them on being distinct, they have to be disjoint. And that's basically what entails a Poisson law. All right, and so to be more precise, let's get into the proof, the method for hyperbolic surfaces. So now you get to say xj, I'm just going to calculate the first moment, by the way, the expectation. if you know that you have a Poisson law, that's all you need. So if xj is my number of simple closed geodesics in a random hyperbolic surface of a given length in a given interval. So first you have to prove that with high probability this curve is non-separating. So this I will sweep it under the rug, but given the fact that it's non-separating here, well, you can do what you can do when you have a curve is you can cut along it. So then you obtain a surface that has genus G minus 1, but now has two boundaries. And so, yeah, we cannot apply like the exactly the counting expectation that I told you about in the previous slides, because we're not counting, but there's something close enough that some people call the Mirzaani integration formula, is that this expectation now is an integral over some volumes of Weil-Petersen volumes. So there's, again, a typo here. There should be a 1/2 in front of it because there's some automorphism factor. And yeah, I didn't tell you that there is a moduli space of surfaces with boundaries, but there is. And then you can calculate this thing. This is where the rescaling is important, because otherwise you're not comparing the same things. And yeah, Mirzaani had proven a lot of asymptotic results that were good enough. So, and then you get the expectation, roughly speaking. So this is very like quick. Of course, there's a lot of technical details that are hidden. You need to prove that the curves are necessarily non-separating with high probability. So if you're interested in the details, just read Bram and Mirzaani's papers. Should be a factor of L? Yeah, okay, yeah, so there's more typos. Yeah, there's a twist factor, yeah. That was just to check if the audience was following, you know, I put this one on purpose. All right, so that's the proof for hyperbolic surfaces, and the proof for maps, it's completely different. It's not this at all. And so, you know, so this afternoon, Guillaume presented the bijection of his PhD advisor, Gilles Schaeffer. So now it's my turn to present the bijection of my PhD advisor, Guillaume. And now I want to tell you about it because it's a very nice bijection. I mean, bijections on maps are always super useful, super powerful. But I don't know, I have the intuition that we haven't like milked the cow to the end. Like there's still stuff to extract from this bijection and to extend to other models. So now you will all know about it. So I start with a map with one face. This is of genus 2, so I just represented it in a planar version, but all you need to know is how it goes around the vertices. And if you want, you can imagine that like every time there's a crossing, it's actually not a crossing, it's like it's jumping above it. So this is how you get an embedding on the surface of genus. Here it's 2. All right, so you have the roots. And what we're going to do is you're going to do the same thing as if you're stuck in a maze. I don't know if you know the trick if you get stuck in a maze, but maybe the trick will save your life one day. If you're stuck in a maze, you just stick your hand to the wall, and then you just walk, and then if the maze is connected, normally you get to the end because you see everything. You see all the pieces of the maze, because basically what is a maze is it's just a tree with a very intricate embedding. So unicellular map in general is just a maze with topology, so a maze of genus something, so a maze with like tunnels and bridges. So anyways, okay, let's get back to the math. So I start from my little root here, and I'm going to go with my right hand on the wall, and when I hit a corner, I'm going to give it a label, just number the corners as they go. So here, this is the corner number 1, and then I continue. So I was here, did this, now I arrive here, corner number 2, corner number 3. So here, you need to be careful, like the intersection is actually not an intersection, so you go under, and you get corner number 4, corner number 5, 6, 7, 8, at some point it's going to stop, yes, all of it. All right. And yeah, so here you have numbered all the corners, and now what you're going to do with that is that you're going to look at the cyclic order around the vertices. how does it go? And what Guillaume calls a trisection is a vertex where the labels are in anti-clockwise order. So basically it's a measure of topology. Imagine you were doing this on a tree. If you do it in your head, you will see that all the edges, the vertices will have their corners in clockwise order. So here there's some defects, there's some trisections. So now I can let you like figure out, I give you like 1 minute to figure out which ones are trisections. It's actually not that hard. It's those here, these boxes in red. And so the bijection of Guillaume now goes this way. What you're going to do is that you're going to choose one. Okay, I forget the corners. You choose one vertex here, one of these trisections, and you're just going to split this vertex in 3. So you get 3 leaves, like so. And you remember just that it came from the red box. All right? And then, well, trust me, you end up with a map with one face, but the genus has been diminished by 1. So now we're in genus 1. Here are the 2 trisections. Trust me again, I don't want to do the numbering again. I'm going to pick one. I'm going to split it. And here I obtain a tree. A tree with all vertices that are of degree 3, except for the leaves, of course. And the leaves are grouped together in like bundles of 3. And, well, the claim is that this is a bijection. So you can go back. Basically, to go back, you just take your leaves and then you glue them together. There's always 2 ways of doing, because there's 2 cyclic orders around the vertex. But there's only one way that will make the genus go up by 1. And so another fact is that if you have genus G, there is always 2G trisections. So that's a little exercise for you. Like, it's not that hard, but not that easy to prove, so it's interesting. But the fact that there are 2G trisections, it means that in genus G, you always have the same number. Whatever the map, whatever you always have the same number, so you have a certain sort of uniformity. And the theorem is that with the bijection, the probabilistic version, of it is that the law of the cubic unicellular maps is just the law of cubic trees when you group the leaves 3 by 3, like uniformly. And what I mean by that is that you can also carry like you get the law of the underlying graph, which is all we need for counting curves. We don't need the embedding. It's just that you can, when you have these cubic trees, you sample the tree at random with the right number of vertices and of leaves. Then you take a random grouping of all the leaves 3 by 3. You just merge them, and you get the cubic unicellular maps. And this is really cool because, maps are a little hard to study probabilistically, but random trees, there's a million papers on random trees. Everyone's a specialist of random trees, so we can do a lot of things. And this is what we use to count cycles. And so here is my map. And in pink, there's a cycle, simple cycle. And through Guillaume's bijection, what is a cycle? It's just a collection of paths with the identifications that are made. So here, this one goes here, this one goes here. So what you need to do now to count cycles is that you need to be able to count paths in trees of a given length and pairs of paths and everything. And fortunately, we can do this very precisely, so that there is a high concentration. And once you can count all of this, you just put this back all together, and you get the result. Again, technicalities swept under the rug. All right. So that's about it for the idea of the proof. I think I went very fast, but that's good. We finish early. A couple last questions. Is that can we use Chapuis bijection? Okay, 1 minute. Is there any questions before I start questions for you? Yes. So if you want a simple cycle, you want the paths to not intersect. And you want the paths listed in some order, such that in the bijection, the endpoint of the first path gets merged by the start of the second point. Yeah, I went very quickly, I'm sorry. And then so on and so forth. And then you have you need to divide by the number of paths because like a cycle, the first path doesn't mean anything, and also by the order, but yeah, basically. But the good thing is that everything is independent. So you count the number of paths, you could like choose your paths, and then afterwards you put the grouping on the vertices. So once you fix your path, now you say, okay, is it gonna work? I can see that you're confused, and that's my fault. yeah. I know that's my fault. But like, yeah, the good thing is that there's a lot of independence. The tree and the grouping of the leaves is completely independent probabilistically. Any more questions? Okay. So what I was saying is that I think there's still stuff to be taken from Chapuis bijection, and especially in other domains of geometry, and maybe in hyperbolic geometry, who knows. So I want to take now the dual of Guillaume's bijection. So the dual of a cubic tree is just a tree of triangles. So here, you have it here. And I color my unpaired edges, again, 3 by 3 by colors. And there is a unique way of gluing, like for instance, for the orange ones, there's a unique way of adding another triangle whose sides are identified with these 3 things, such that the genus goes up by 1. So basically, you can do the same in dual, and you can build from a tree of triangles. You can build a surface, any surface that you want. In this fashion. Of course, yeah, if you want your surface to be flat, to not have conical singularities, there is some trouble about the angles, so there's a lot of conditions that are annoying. But I mean, there's a lot of ways to circumvent that. For instance, you can take hyperbolic ideal triangles, so they all have angle 0, and then you glue them, and let's say you don't want shear, so the shear was defined, I guess, in Catherine's talk. So if you do it without shear, then there's no compatibility conditions, and then you do all this bijection here, and you obtain a hyperbolic surface with exactly 1 cusp. And that's just a Brooks-Macover model when you restrict it to have only 1 cusp. Yeah? Oh, yeah. The boundary has to be a multiple of 3. But also here, sorry that I didn't mention, but the number of leaves has to be a multiple of 3. Otherwise, you cannot do anything. Yeah. So sorry, I'm always going too fast, but that's what I meant when I say the right number of vertices, or the right number of triangles. Yeah, but good point. So the easiest thing to do is like ideal triangles without shear, so there's going to be a unique singularity because it's a dual of maps with 1 face, so it has only 1 cusp, and it's Brooks-Macover with 1 cusp. I don't know if it's helpful. I haven't investigated the subject, but I guess there's other ways to use this bijection, so maybe you have ideas. And yeah, I guess I'm almost done. So that's for that talk was like 1 result and a lot of questions that I cannot answer, but I gave you like all I could say. This was probability. Now I just want to tell you a little bit about enumeration. Just a bonus question before we go. So with Thomas, we proved this asymptotic expansion of number of triangulations of genus G and 2n triangles. So it goes like n over 2g, n to the 2g times a certain exponential with a certain like function. Can we do the same for Weil-Petersen volumes? So we know that the volume of Weil-Petersen mgn, when g and n are going, n over g goes to a constant, theta, that it still starts with n over 2g, but I think we don't know anything else. my best guess would be that there is another function that we can describe explicitly that explains the behavior. I have no idea how to prove it, but again, I mean, that seems quite natural. All right, and I'm done. Thanks.
Thank you. Do we have more questions? Gregory.
Yeah, concerning your last question, is there some hope that it can follow from similar arguments, the one you have with Thomas, or is there an obstruction to that?
I mean, we kind of have like said that maybe one day we should look at the local limit of Val-Petersen surfaces when you have like a lot of cusps. And hopefully maybe that would follow from this, but there's a lot of technical issues that I mean, we haven't started even like writing stuff down, so I think it's also still very hard. So, but that could work. Yeah, I don't know.
Yeah, I guess the analog of the recursion formulas that you have for KP are known in this situation. I mean,
I don't think so. I'm not aware of a formula like KP style formula for volumes.
okay.
I don't know. Like there's experts of the moduli space in this room, and none of them seem to want to say anything. So I guess it's not known. Yeah. I don't know. I don't think there is.
Thank you.
Another question? So in the unicellular case, so you showed your result with the count of cycles of given length. Are there any other observables that you can compute and that you suspect would be the same as?
Yes, so with Fante, we did a calculation once. There was like this conjecture of, that's now a theorem of Yu Hao, who's here, and that if you take a curve of length smaller of square root g, then most probably it doesn't self-intersect. And then above square root g, so if it's like grows much faster than square root g, then it self-intersects like with high probability. And so we had done the calculation, and it seemed to be like the case also in our setting. But we really did like back on the envelope. This is not written anywhere, and it's not meant to be written anywhere. So there's no trace of this.
Thank you. Any other question? Okay, so well, thank you again.